Alright, so moving on from the last video, we want to focus on now on the hyperbolic. So let's recall that the hyperbolic cosine function is given by half e to the x plus half e to the negative x. Let me first point out two facts. One is when x is big, then notice that e to the negative x is small. So the graph of hyperbolic cosine would be approximately half e to the x. And when x is large negative, e to the x would be close to 0. And so hyperbolic cosine of x would be close to half e to the negative x when x is large negative. So and the graph of so the graph of the hyperbolic cosine function is here in pink, and this is the graph of half e to the x right here, and this is the graph of half e to the negative x right here, and they intersect at height at the point 0, half. And hyperbolic cosine function is the sum of these two exponential functions. So basically the height of the hyperbolic sine graph is the sum of the heights of the two exponential functions at any x. So right here is the height of half e to the x, and right here is the height of half e to the negative x. So when you add these two heights, you get the height of the graph of hyperbolic cosine of x. Alright, so the pink one is the graph of the hyperbolic cosine of x. Now clearly it is not a one-to-one function. So you know, on the entire set of real numbers it's not one-to-one, but what we're going to make it one-to-one by just choosing by just restricting x to be a non-negative. So if we take the domain from 0 to infinity, then we get this part of the graph right here, and then it's one-to-one, and then the inverse of that, the graph of the inverse of this part is this green curve right here. So this is the reflection of the graph of hyperbolic cosine across this line. Now notice that I have the point 0, 1 right here, and that's reflected on the point to the point 1, 0 right here. So this green curve is the graph of the hyperbolic cosine inverse of x, and again, to define the inverse of the hyperbolic cosine, we had to restrict its domain from 0 to infinity. Now notice that by restricting its domain from 0 to infinity, we didn't lose any of the values in its range. The range of this function, the range of hyperbolic cosine is still from 1 to infinity. So a hyperbolic cosine inverse of x is y if and only if hyperbolic cosine of y is x. The domain of the hyperbolic cosine inverse of x would be from 1 to infinity. So here the domain of this function is from 1 to infinity, and the range of the hyperbolic cosine inverse of x is from 0 to infinity. So the range of this function is from 0 to infinity, and again, the domain of hyperbolic cosine inverse is the same as the range of hyperbolic cosine, which are the same, 1 to infinity. And the range of hyperbolic cosine inverse is this, and that's the restricted domain of the hyperbolic cosine, where it is 1 to 1 and yet keeps its entire range. Okay, so the cancellation properties. So these two functions are inverses. So when you take the composition of these two functions in any order, we get the identity function. So the first equation is valid for x in the domain of the hyperbolic cosine inverse of a inverse function. So x has to be greater than or equal to 1. And the second equation is true for x in the for x greater than or equal to 0. A hyperbolic cosine of 0 is 1, and as a result the hyperbolic cosine inverse of 1 is 0. And one can easily calculate what that is. Let me make some room here to see why that's the case. Okay, so hyperbolic cosine x is e to the x plus e to the minus x over 2. So clearly when x is 0, in the numerator we would be getting e to the 0 plus e to the 0, and e to the 0 is 1, so in the numerator will be 2 when x is 0, and then we end up with 1. So hyperbolic cosine of 0 is 1, and as a result the hyperbolic cosine inverse of 1 is 0. Now hyperbolic cosine of ln of 2, what's that? So notice that the hyperbolic cosine of ln of 2, well, that's going to be e to the power ln of 2 plus e to the power minus ln of 2 divided by 2. Now the point here is the e to the ln of 2 is just 2, and e to the negative ln of 2 is actually half. Now the reason is the negative ln of 2 is the same as ln of 2 to the negative 1. So this is equal to e to the ln of 2 is just going to be 2 plus, and this is e to the ln of 2 to the negative 1. This is by using one of the properties. Okay, let me open up the file again. Okay, so what I was writing then here is we get 2 plus e to the ln of 2 to the negative 1. This is by one of the, so here I have negative 1, and that can be by one of the log properties. We can do this, and then e to the ln of 2 to the negative 1 is just 2 to the negative 1, but 2 to the negative 1 is half, so this is going to be 2 plus a half over 2, and that is the same as 5 divided by 4. So hyperbolic cosine of ln of 2 is 5 over 4. As a result, the hyperbolic cosine inverse of 5 over 4 is ln of 2. Okay, so that's all I wanted to say about the hyperbolic cosine and its inverse function. We have already seen its we have already looked at its derivative formula. Okay, so now I want to look at the graph of the hyperbolic tangent function. So the hyperbolic tangent function is evaluated at x is given by e to the x minus e to the minus x over e to the x plus e to the minus x. Now as x goes to infinity, notice e to the negative x goes to 0. Okay, so what I'm claiming is that the hyperbolic tangent function has limit 1 as x goes to infinity, and it has limit negative 1 as x goes to negative infinity. So these are actual limits of this function. So the way to see it is that, so I have this e to the x minus e to the minus x over e to the x plus e to the minus x. That's the hyperbolic tangent function. I'm going to factor out e to the x from the numerator, and also factor out e to the x from the denominator. And if I do that, I get e to the x times 1 minus e to the negative 2x. So when you factor out e to the x from the numerator, you have to multiply each term with e to the negative minus x. So when I multiply this with e to the minus x, I'm going to get 1. When I multiply this with e to the minus x, I get e to the negative 2x. So that's the effect of factoring out e to the x. Similarly here, when I factor out e to the x, I get 1 plus e to the negative 2x in the parentheses. E to the x cancels out, so I end up with this only right here when I cancel this out. Now, another thing that I could have done is, so this is what I need to do in order to see what's the limit as x goes to infinity. So notice that as x goes to infinity now, the e to the negative 2x goes to 0, right, because of the negative exponent. So when x goes to infinity, the exponent here goes to negative infinity, so this term goes to 0. Similarly, this term goes to 0, so you end up with 1 over 1, so the limit is 1 when as x goes to infinity. On the other hand, to see that the limit is negative 1 when x goes to negative infinity, we now have to, instead of factoring out, so here I factored out e to the x, now I'm going to factor out e to the negative x. So here, if I factor out e to the negative x, then I have to multiply each term by e to the positive x. So if I multiply this by e to the positive x, I get e to the 2x. If I multiply this with e to the positive x, I get 1. Similarly in the denominator. So if I factor out e to the negative x, then I get this expression right here. Once again, after we cancel out what we have factored out, we can now see what the limit is. So you can see when x goes to negative infinity, the exponent here goes to negative infinity, and e to the 2x then will go to 0. Similarly, this one goes to 0, so then we end up with negative 1 over 1, and then the limit is negative 1. So again, the point is, as x goes to negative infinity, the limit of hyperbolic tangent of x is negative 1. As x goes to positive infinity, the limit of hyperbolic tangent of x is 1. Let's recall that the derivative of the hyperbolic tangent of x is secant squared of x. Being positive, we see that this function is an increasing function, on its entire domain. Okay, so this is an increasing function, and we can also look at the second derivative of this function. If I take the second derivative, that's going to be the derivative of the derivative. So what's the derivative of hyperbolic secant squared of x? Well, that's going to be 2 hyperbolic secant of x times the derivative of hyperbolic secant of x. And okay, so let me write some. So we are taking the derivative of the hyperbolic secant squared. So by chain rule, we're going to get 2 times the hyperbolic secant of x, and then I have to multiply that by the derivative of, so this function here is hyperbolic secant x to the 2, right? So when I take the derivative, I get 2 hyperbolic secant of x, and then I have to multiply by its derivative, multiply by the derivative of the inside, which is the secant of x, hyperbolic secant of x. So the derivative of the hyperbolic secant of x, if you recall, is negative hyperbolic secant of x, and then tangent, hyperbolic tangent of x. So you can see where I'm getting this negative 2 hyperbolic secant squared of x times hyperbolic tangent of x. So again, that's the second derivative of the hyperbolic tangent of x. In other words, that's the derivative of the square of the hyperbolic secant of x. All right, so notice that this second derivative is clearly positive when x is negative, and it's negative when x is positive. Why? Because okay, the hyperbolic secant squared, we know that that's just positive because of the square. Now hyperbolic tangent, we know that it is if you look at the hyperbolic tangent of x formula right here, you can see that it is this divided by that, right? So the denominator here is always positive. So the sign will be determined by the numerator, and then if you look at the numerator, it is positive when x is positive, and it is negative when x is negative. So when x is negative, a hyperbolic tangent of x is negative, and then we have a -2 here, so that makes it positive. And similarly, when x is positive, hyperbolic tangent of x is positive, and because of the negative, we get negative here. So that means the second derivative of the hyperbolic tangent of x is positive and negative according as x is negative or positive. So it tells us that the hyperbolic tangent of x is concave up when x is negative, and it's concave down when x is positive. So putting together all this information, we can get that the graph of the hyperbolic tangent of x is, we know that it's increasing everywhere. We know that it has a horizontal asymptote at -1 because as x goes to -infinity. So remember we did this. As x goes to -infinity, the limit is -1. So that's so then that tells me that y is equal to -1 is the horizontal asymptote, and the first limit tells me that y is 1 is a horizontal asymptote. So it is increasing. It has horizontal asymptotes, so y equals to -1 and y equals to +1. And we know that the hyperbolic tangent of 0 is 0. It passes through 0. It is concave down when x is positive and concave up when x is negative. So we get this graph. Now it is a increasing function, so it is 1-to-1, so it has an inverse, and the graph of its inverse will be the reflection of it across the line y is equal to x right here. So this is the pink one is the graph of the hyperbolic tangent inverse of x. So one thing I want you to notice here is that notice that the inverse of the hyperbolic tangent has vertical asymptotes at -1 and 1, and the hyperbolic tangent has horizontal asymptotes at -1 and 1. Okay, so hyperbolic tangent inverse of x is y if and only if hyperbolic tangent of y is x, because it's the inverse. And the domain of the hyperbolic, so if you look at the range of the hyperbolic tangent, right? The range is from -1 to 1 for hyperbolic tangent of x, and the domain is the set of all real numbers. So the domain of the hyperbolic tangent inverse of x is from -1 to 1, and the range of the hyperbolic tangent inverse is the set of all real numbers. And of course, the cancellation laws for inverse functions hold here. So hyperbolic tangent inverse of x is x, and hyperbolic tangent inverse of hyperbolic tangent of x is x. In the first equation, x is in the domain of the hyperbolic tangent inverse, so it is between -1 and 1. And in the second equation, x is any real number. Okay, so I'm going to stop the video here, and in the next video we will be looking at some explicit formulas for the inverse hyperbolic functions, and then we will be also looking at the derivatives of the inverse hyperbolic functions and some other facts. Okay, so I'll stop here, and I'll see you in the next video.